Let's look at an application of the second partials test. This example you'll find in your lecture notes, and it deserves some attention basically because it utilizes the same techniques that you've used before. However, there's more complication in the analysis. And we find that to be true in calculus. If you recall doing optimization problems in calculus 1, they could be extremely lengthy. Not only were you tasked with determining the actual function, then you had to analyze the function. So that turned out to be a long process. Here, we will start with the function and utilize the ideas that we have already in understanding how we can actually get to some extreme values. So now what we want to do is examine the following function for relative extrema and saddle points. Notice here, instead of just a polynomial in x and y, we have the product of a polynomial and an exponential function. And this is not an absolute extrema problem. We are given the entire real plane for x and y. And again, you can see with the negative here by the x squared term that hopefully that will indicate the existence of some critical points that we can analyze. Now, just like before, we want to solve the system, the x partial equal to 0 and the y partial equal to 0. That system will give us critical points if they exist. So now, of course, notice here you've got the product rule, that is the algebraic function times the exponential function. So we just use the product rule for differentiation. So again, we have an x partial here to give us a negative 2x. And then, of course, the derivative of the exponential function is itself times the derivative of the power, in this case, which is just a negative 2x. So how you decide to factor at this point is completely up to you. I have certain ways that I've done this to make the problem a little easier, but again, this is completely your choice. So notice here, we've got negative 2x and a negative 2x in both cases, which we can factor, and also the exponential term. So upon doing that, we get the 1 from this particular term here. And then, of course, we get all of the factors that live by this term, 1/2 minus x squared plus y squared. And then at this point, it is completely up to you. You can run the negative inside. We certainly don't need to run the 2 in, but we can run the negative, and that'll give us a positive x squared, a negative y squared, and then a negative 3/2 here. So again, this type of analysis is completely up to you. We certainly have a product and we want to make use of that, but how you move constants around is completely up to you. So now notice we have a 0 product, the exponential term never being 0. Of course, you learned that in pre-cal when you didn't know very much. And then, of course, 2x can be 0 if and only if x is 0. And then, of course, this polynomial in x and y can be 0 if and only if x squared minus y squared equals 3/2. So again, simple analysis, 0 product. We have 2 possibilities with the fx equals 0 equation. So now to finish the analysis, we need to do the same for the y partial. So again, we do exactly the same before, getting a 2y upon differentiation here in the first factor. And then with the second factor, what we see is we get the exponential term, the algebraic expression, and then, of course, a minus 2y. Now, at this point, again, your choice. What I've done here is I've just run the negative inside here to have a common 2y and exponential term here to make the algebra a little bit simpler. So, of course, this gives us a negative 1/2, a positive x squared, and a negative y squared. And then, of course, when you add the terms, you get the following expression, x squared minus y squared plus 1/2. Again, 0 product. So now, of course, the exponential term not being 0, we could have 2y equals 0, which gives us y equals 0. Or we can have the polynomial in x and y being 0, which would be equivalent to x squared minus y squared equals -1/2. Now we've got basically a counting problem. You have two results from each partial derivative equation, so you just pair them up. So first, if you want to start by pairing the y equals 0 with x equals 0, we just get the critical point 0, 0. Very simple. And now we compare y equals 0 with x squared minus y squared equals 3/2. So of course that would mean the y squared term is 0, and that leaves us with x squared equals 3/2. So now you can just use square root property and get x as plus or minus square root 3/2. So that gives us two critical points. Now we can flip it around and say, okay, well, what can we do now? Notice we can look at the top box and just go ahead and compare x equals 0 with the polynomial in x and y. Of course, now if x is 0, we're left with negative y squared equals -1/2. And of course, the negatives absorb. And so now by the square root property, y would just be plus or minus the square root of 1 over root 2. Or just the square root of 1/2, which gives us what? Plus or minus 1 over root 2. So notice here, by the square root property, we get two critical points here, two critical points here, and a critical point here. The last pairing would just be the two algebraic expressions, but we know that's inconsistent. We have x squared minus y squared equals 3/2, and x squared minus y squared equals -1/2. And of course, that's inconsistent. That will not give us anything. So we have no solution here. Now, the idea here is just like before. We solve the system of the partial derivatives set to 0 in order to find any critical points. Now we see we have 5. The second part of the analysis with the second partials test is to look at the second order partials, just like you had to compute on your second test. So when you do that, you think, okay, well, our derivatives are much more complicated. So what we can do is streamline the process without having to write down a specific formula. We've got the fairly straightforward critical points, and they have zeros in them. So that's going to make the analysis much easier. So notice I've dictated down here at the bottom the formula for the D in the second partials test. So once we have these particular second order partials, we can just evaluate them and then construct the D from that without having to write a general formula, which would really be a waste of time. So what we do is we take the derivatives that we've already computed, the x partial, to take the second x partial. Again, we have the 2 factored. So again, we just do the same procedure where we do the product rule. Again, just like we did before, notice 2 is multiplying both of these expressions. Now, at this point, we want to be able to utilize the fact that we have a common exponential factor. Notice we don't have the 2x running around over here, so you can simply absorb, in this case, the -2x into this expression here. So notice we have the 3x squared, the minus y squared, and the -3/2. And then upon multiplying by the -2x, we get a -2x to the 4th plus 2x squared y squared plus 3x squared. So now we've got a simple equation, the 2 still hanging out, but that's no big deal. But again, we want an exact expression for f(x)(x). When I say it's no big deal, we can just leave it as multiplied by 2, or we could run it in. Your choice. What I decided to do to make it a little bit cleaner is just go ahead and run the 2 inside, and we get a 12x squared minus 2y squared minus 3 minus 4x to the 4th plus 4x squared y squared. Again, just multiplying by the 2. And that gives us a formula for the second order partial relative to x. This is what I was talking about before. We don't need a general formula. We just need this second order partial. Now, in summary, you can do the same thing for the second order y partial and the mixed partial. Same analysis, just like I did before. And one thing with the notation, I'm using a subscript with the brackets here to notate an x partial. Again, here I use the subscript y to notate a y partial. And then for the mixed partial, we just take the derivative of the x partial relative to y. So that technique you're very aware of. And so what I've done here is I've simply written at least a neat expression for all of the second order partials. And then, of course, as I said before, reminded us what these should be. So even though this analysis is more long-winded, like your professor, it's very straightforward algebra. Again, we just need to figure out what the sign of these particular expressions happens to be. And in the most particular case, just find a value and multiply. So in the very last analysis, and what I've done here is I've tried to summarize everything that we have on the previous page so we can easily allude to it. We have the original function here, and then I've just written the second order partials. So remember, for the second partials test, we've got to figure out the sign of the second order partial relative to x, and then the sign of d. Then we can move forward with an interpretation of that. So let's do the easiest one first. And like I wrote here, even powers make the analysis quicker. Absolutely. No pun intended. And then when you have zeros, I wrote added bonus. We love zeros because, you know, they're so easy to evaluate. I mean, we can use any number we like. It doesn't change the evaluation procedure. It just makes it simpler. Now, with the zero here, we can go through and look at the second order partial relative to x. All of these terms would be zero save the -3. So we just get what? Again, 0, 0, e times a -3. That's less than 0. Okay, so we've got that clearly. For the y second order partial, we can do the same thing. All of these terms with the x's and y's go away, and we're left with a 1 and an e. So we just have e. And then for the second order partial, notice all of these factors have x's and y's. So that just goes away. That's annihilated. We get a 0. So now what you see here is that when we look at the value of d, we have the second order partial with x and y multiplied to give us a negative number, okay? So when d is negative, automatically saddle. So we have a saddle point. Again, what's the actual value of the function? Well, we can simply substitute 0 in for x and y, and we just get 1/2 e. So like we've done before, even though it's not completely correct, I mean, we just need the value. The extreme value is the value of the function, but we like to notate where it occurs, and we just do the ordered triple, just like doing an ordered two-tuple in calculus 1. So we have 0, 0, e divided by 2. That's a saddle point. So again, like I said before, the analysis is just like what you've been doing before. It's just longer. Now, when we do the other critical points, we've got the plus or minus square root of 3/2, comma 0. Again, this will be easy using the even powers. So notice here, all of the y's are 0. So if we do f(x(x), all of the y's here, any term that has a y in it just goes away to 0. And then, of course, with the even powers, we get very simple algebra and arithmetic going on there. So upon doing that, we get the 12 times the 3/2 minus the 3 minus the 4 times the 9/4. Now this will reduce, we've got these nice numbers here, such a gift. We end up with 6 times e to the minus 3 halves. Notice when we square the x, we just get the 3 halves, and when we raise it to the 4th power, we just get 9/4. You can do those in your head. And so now notice we just realize here that 6 times e to the -1/2 is a positive number. Again, we don't worry about what it is, we just know it's positive. And now we can do the same with the second order y partial, same type of analysis. We get 4e to the -1/2. And then with the second order partial, again, we look through here, all of the terms that have the 0 in them are just everything. I mean, that goes away. So we like the mixed partial because 0, we don't get anything. It gets annihilated. So now when we take the product of the second order partial relative to x and the second order partial relative to y, we get a 24e to the -1. So now that's a positive number. Comparing this to the second order x partial, which is positive, this will give us a relative min. Now, of course, if we analyze z at this particular critical number, you can see here, as we run in the plus or minus square root of 3 halves, this will just give us 1/2 minus 3 halves. And so that just gives us a -1 here. And then, of course, the exponential term is e to the -1/2. So the actual value of the function is -e to the -1/2. And that is, by the second partials test, a relative minimum. Now, for the last one, again, you see the technique here. We're going to look at the critical points, 0 plus or minus 1 over square root of 2. And again, we can use the same analysis. Because the x is 0, that makes everything very simple. Notice with the value of z, we're just, in this particular case, we're just going to get 1/2 plus 1/2. And so, of course, 1/2 plus 1/2 is 1. So the value of the function will be e to the 1/2. Well, does this have a particular character? Is it a min, a max, a saddle point? So when you actually compute the values of the second order partials, not a surprise, the mixed partial is 0, as we would think it would be, but the second order x partial is -4e to the 1/2, which is negative. And then the second order y partial, again, by a similar analysis, is -2e to the 1/2. Again, when you consider how we've done this problem, and again, the existence of even powers and zeros, even powers in the second order partials and zeros in the critical points, it makes the analysis a little bit more streamlined. But now when we notice this, we have a negative second order x partial, and then we have a positive d in this case. That will give us, by the second partials test, a relative maximum. So again, I wanted to point out here that you don't have to shy away from more complicated functions. The analysis is the same. However, it is certainly more tedious when you have more complicated functions. The results and everything that you do are just predicated on particular signs that you develop as you work through the analysis. So again, in summary, at the critical point 0, 0, we get a saddle point. At the critical points, plus or minus 3 halves or square root of 3 halves, comma 0, we get relative minima. And at the critical points 0 plus or minus 1 over the square root of 2, we get relative maximum. And we are done.